Okay, so I posted midterm scores, and by and large, most of you did very well. Um, some of us did not do as well, and that's okay. So the well, okay. So all right, let me say a few things. Okay, first of all, it's just a midterm. Okay, and then okay. Well, most importantly, your value as a person, who you are. You guys laugh, but I'm totally sincere and serious here. Okay, your value as a person, who you are, is not determined by your scores on a test, scores on a midterm. It's not determined by what people have to say about you. You are valuable and important in of yourself. Okay, you don't need a midterm exam to say how good or bad you are. Okay. But I know it feels good to score well, and it feels bad to score poorly. I understand that. But okay, so the median was a 28 out of 31, which puts the median at like 90%. I was like, oh wow, that's really high. So good job, you guys. Or maybe I made this test too easy, but I like to think that you guys all studied hard and did really well. And then the first quartile was like at 84%. So about 75% of you scored over that. So that's good. Some of us scored down here, and it might not feel so great to be down here, and that's okay. Again, the scores don't determine your value, and I think if you scored, I would say over 20, we can probably just with a little bit of effort and if you come during office hours, I'm more than happy to help and to help you get things turned around. Okay, if you're a graduating senior and you're kind of in this zone, please come talk to me. We'll come up with a game plan to make sure you pass the course and we don't hinder your academic progress. A handful of us score down here, and I'm a little bit more concerned about kind of these sub 20 scores. And so if this is you, please come talk to me, and we'll try to find out what's working or what's not working, and we'll try to get you we'll talk about what our options are and what the best thing to do would be. So it is the 5th week, but it's not too late. We still got 6 weeks left in the quarter. We can turn things around. We can get things better. But I can only help you if you come asking me for help, right? If you're struggling, but you're just don't be too embarrassed to come and ask for help or anything like that. I know sometimes it doesn't feel good to be down here. I understand that, and so it's easy to just kind of want to stay hidden, but that's not going to be helpful. So come talk, and we'll talk about our options. See what we might be able to do to get us to improve. So anyway. That's all I want to say about that. You guys do have a quiz tomorrow. Wait, no. This class is Thursday, right? Okay, so you guys have a quiz this week on Thursday, sorry. And that will cover through today's lecture content. So I'll cover some new material today on probability, and your quiz will cover up through that. So chapter 5 stuff. Okay, well, we'll get started on today's content. We're talking, we're still in probability. And so far in probability, we've covered OR rules. We've covered what it means to be mutually exclusive. what it means to be independent. Oh, here's a question. Here, we'll start off with a clicker question. Okay, so we'll say two events, A and B, are mutually exclusive. And they both have non-zero probabilities. So okay, so the question is, could A and B be independent? Okay, and the answer choices are A, yes, they could be, but are not necessarily, but are not necessarily independent. Okay, B is yes, they are definitely independent. And C is no, they are certainly not independent. Okay, let's get the clicker software going. Okay, so two events, A and B, are mutually exclusive. They both have non-zero probabilities. Could A and B be independent? And so A is yes, they could, but are not necessarily independent. Could be, but are not necessarily independent. B is yes, they are definitely independent, and C is no, they are certainly not independent. Okay, so talk this over with your neighbor. What do you think? Talk about the definitions of mutually exclusive and independent. See what you think. Get your clicks in. I'm going to click stop here in just a minute. Not a minute, just a moment. Oh, there's only 133 of us today. Okay, well, all right, I'll hit stop. Let's see what you guys came up with. Okay. The correct answer choice is C. Okay. All right. Let's talk about this. Okay. Yeah. Okay. So A and B are mutually exclusive. What does it mean to be mutually exclusive? All right. So mutually exclusive means the probability of A and B equals 0, right? This means the probability of A and B is equal to 0, meaning if A happens, then B is impossible. Okay. All right, independent means the probability of B given A, this is equal to just what? The probability of B, right? If A happens, it has no impact on the probability of B happening. Meaning probability of B is just the probability of B. Probability of B given A is just probability of B. So if two things are mutually exclusive, that means if A happens, it makes B impossible. That means there is an association between whether A has happened and the probability of B happening. Okay? So if A has happened and that makes B impossible, then that means they are certainly not independent. Okay? Because independent would mean that if A has happened, the probability of B happening is just the probability of B. If they're mutually exclusive, if A has happened, that makes the probability of B happening to be equal to 0. Right? So you know, making something impossible means it can't be independent. Independent means it has no influence on the outcome of the other. Does that make sense? All right. So yes, question. Yeah, if we're talking about two coin flips and we're talking about the outcome of the first and the outcome of the second, then yes, the outcome of the first has nothing to do with the outcome of the second coin flip. Those coin flips are independent. Okay, so if we say the probability of the coin landing heads on the first one is 0.5, and the probability of the coin landing tails on the second one is also 0.5, you know, we ask, well, what's the probability that the coin lands tails on the second coin flip? We say that's 0.5, okay? That means A and B are independent in that case. Mutually exclusive is a different scenario. That would be something like the coin lands heads on the first and the coin lands tails on the first, okay? On the first coin flip, either it lands heads or it lands tails. It cannot land both. So those would be mutually exclusive outcomes, right? If I tell you the coin has landed heads on the first coin flip, you know for a fact that the coin did not land tails on the first coin flip, okay? So whether it landed heads or tails on the first coin flip are mutually exclusive. Whether it lands heads or tails on the first and whether it lands heads or tails on the second, those are independent. No, well, it doesn't matter whether I say there's a first or second trial. Here, it's just two events A and B are mutually exclusive, okay? So mutually exclusive means the outcome of one and the outcome of the other cannot happen together. So in that case, A and B, if I say A and B are mutually exclusive, it cannot be a scenario where they're independent, okay? It cannot be a scenario where A is talking about the first trial and B is talking about the second trial, because the fact that I said A and B are mutually exclusive basically precludes their independence. Okay, that's kind of that was the point of this question. If you know two things are mutually exclusive, and we're avoiding the kind of the trivial situation where A and B have zero probabilities of 0, then we would say that they are not independent if we know that they are mutually exclusive. Okay. That took a loop. So anyway, we covered mutually exclusive events. We've covered independent events. We've covered probabilities of OR situations and conditional probabilities. And now I want to focus a little bit more on independent events and in particular sequences of independent events. Okay, so probabilities. Sequences of independent events. Okay, probabilities for sequences of independent events. So let's say events A and B are now independent events. Okay, so now we're talking about two different events, A and B, and they are independent. Okay, that means, this means the probability of B given A is equal to what? The probability of B, right? And from before, so from Wednesday's lecture, we learned that the probability of A and B is equal to the probability of A times the probability of B given A. Right? And I'm hoping this is semi-familiar. We might have forgotten this, but I'm reminding you that this should be in your notes from Wednesday. Maybe I have the letters A and B switched around, okay? But the labels A and B, those are arbitrary. So, you know, if I called one thing A and this thing B in one scenario, and in the other scenario I called this one A and this one B, it doesn't matter. The labels A and B are arbitrary, okay? So we have probability A and B is equal to this. If they're independent, then this thing boils down to this, right? So if when A and B are independent. Okay, so this boils down to probability of A and B is equal to the probability of A times the probability of B. Okay, so this is true for independent events. Okay, and then this can further be generalized to, you know, if you have a bunch of events, if you have events A, B, C, and D are all independent, then the probability of A and B and C and D is equal to the probability of A times the probability of B times the probability of C times the probability of D. Okay? You just multiply them all together. Okay, and this is true if they're all independent. It doesn't work if they're not independent. Okay, if we're talking about flight delays and the weather, those are not independent events. You can't just multiply stuff together. Okay, but if we're talking about coin flips, sequences of coin flips, or rolling a die or something like that, those are all independent. We can treat them as such, and we can just multiply them all together. All right, so let's try an example here. We will say we find some special coin. There are debates as to such a special coin, if this thing could even exist. We find a special coin that has a probability of landing heads equal to 0.7. Okay, so when you flip the coin, it will land heads with probability 0.7. So the question is, I flip the coin twice. What is the probability it lands heads both times? Okay, and then we will say each coin flip is independent. Yeah, we'll say each coin flip is independent of previous flips. Okay, well, what we say is this means we need the probability of heads on the first flip and heads on the second flip. Heads on the first, heads on the second, so this will be probability of heads on first flip times probability of heads on the second flip. Okay, because they are independent. So probability of heads on the first, 0.7 times the probability of heads on the second, also 0.7, so this multiplies out to 0.49. So I'm just going to write probability of heads and then heads. I'm just going to abbreviate this heads on the first and heads on the second to H, comma H, 0.49. Okay, what is the probability of heads on the first and tails on the second? Okay. So our answer there would be probability of heads then tails, which is going to be probability of heads times probability of tails. 0.7, and what's the probability of tails? 0.3. So I get 0.21. Heads on the first and tails on the second, that is different from what is the probability of tails on the first and heads on the second. Okay, the probability ends up being the same, but the outcome tails heads is different from heads tails. Okay, perhaps the resulting probability ends up being the same, but they are different outcomes. Okay, it's the difference between a family that has two kids, one boy and one girl. It's the difference between the older sibling being the boy versus the older sibling being a girl. Okay, maybe the net probabilities, and perhaps if we're just counting how many boys and girls there are in the family, it might seem the same, but they are different scenarios, right? So getting heads on the first and tails on the second is different from tails on the first and heads on the second. So we have to, they are different outcomes. Okay. Is this all good? Okay, we'll try giving you a question here, okay? So I'll say, I flip the coin twice. Okay, and I'm going to say, what is the total probability? So again, what is the total probability that after two flips, the coin lands the same way, both times. Okay. Maybe I need to clarify. So, and I will say probability of heads for one flip is still equal to 0.7. All right. So our answer choices will be 0.49, 0.21. 2. Okay. Lands the same way both times. So, I don't know, maybe this makes sense or this doesn't make sense. So this means if you think about it, okay, you can get heads, 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 tails, tails, heads, or tails, tails, and landing the same way both times would be heads, heads, and tails, tails, right? Okay. Okay, so go ahead and compute this out. If you need to consult your neighbor. All right, I'm going to go ahead and click stop here. So if you haven't clicked, click. Okay, so that is correct. Answer choice D is the correct answer. So as you guys figured out, the probability of both times means heads heads or tails tails, right? So these are mutually exclusive. Heads heads and tails tails. These outcomes are mutually exclusive. It is not possible for the coin to have landed heads heads and at the same time have landed tails tails. That's not possible. So because of that, I can just do probability of heads heads plus the probability of tails tails. I don't have to worry about subtracting some kind of overlap. There's no overlap between the outcomes heads heads and tails tails. Probability of heads heads becomes the probability of heads times the probability of heads, because the first and second coin flips are independent. And over here I have the probability of tails times the probability of tails, because again the first and second coin flips are independent. Therefore my answer ends up being 0.7 times 0.7 plus 0.3 times 0.3. I get 0.49 plus 0.09, and this adds up to 0.58. Probability of heads heads or tails tails. Okay, that seems reasonable, I think. Let's try a few more. Let's do a few more examples here. So we'll continue using our special coin still. Special coin which has probability of heads equal to 0.7. Okay, so this time I will flip the coin flip the coin 4 times, and the question is, what is the probability I get heads 3 times and the last flip is tails? Okay. What is the sequence that has to happen here? The sequence goes what? Heads, then heads. So this is the first, the second, the third is going to be heads, and then the fourth is tails. Okay, so I just do 0.7 times 0.7 times 0.7 times 0.3, yeah? So this ends up being 0.7 raised to the third times 0.3, technically raised to a 1. Is that okay? And I need my calculator. Somehow my computer calculator stopped working. So 0.7 raised to the third times 0.3, I get 0.1029. Is that okay? Okay. This is a different question. Let me ask a similar sounding but different question. This will be, I flip the coin 4 times. And the question is, what is the probability I get heads 3 times and tails 1 time? Okay. And there's kind of an implicit, this implies, because order has not been specified, implicitly, order does not matter. Okay. So in this scenario, I have different outcomes that I have to consider. Okay. So one of them I calculated heads, 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 tails. Basically tails on the fourth. And then there's also the scenario where I get heads, heads, tails, heads, heads, tails, heads, heads, and tails, heads, heads, heads. Is that okay? And for each of these, this probability was 0.7 raised to the third times 0.3, and I got 0.1029. What's this probability going to be? Heads, heads, tails, heads. Okay, well, it's going to be 0.7 times 0.7 times 0.3 times 0.7, right? Technically. But because multiplication, the order doesn't matter, this all boils down again to 0.7 to the third times 0.3. And I get 0.1029. Is that okay with everybody? All right, and then so we can apply that logic to here, 0.1029 and 0.1029. And all of these outcomes, they are mutually exclusive from each other, right? There's no like I can't get this scenario and this other, I can't get tails on the last one and heads on the first three and have at the same time gotten tails on the first and heads on the last three. So the total probability of this thing ends up just being, so the probability of 3 heads and 1 tails, order doesn't matter, ends up being 0.1029 times 4. So 4 times 0.1029 gives me 0.4116, 0.4116. Okay, that's kind of a complicated problem. This is known as a binomial problem. We're going to cover this more in depth on Wednesday, okay? This is binomial. This will not be on the quiz. No quiz. Okay? But we will cover this in depth on later this week. Okay? This scenario. This is different from, so one more outcome that will make it on the quiz, okay? All right, so again, we're still dealing with our special coin that has probability of landing heads equal to 0.7. So I'm going to say I flip the coin 4 times. Flip the coin 4 times. All right, and the question is, what is the probability I get tails at least one time? At least one time. Tails at least one time. So what does that mean? At least one means one or more, right? So I want, what's the probability I get one or more tails? Okay, so this means, what is the probability I get one or more tails? Okay, so I'm going to just say this is the probability of 1 or 2 or 3 or 4 tails. Okay, and I can't get more than 4 tails because I'm flipping the coin only 4 times, so that covers all of my outcomes here, right? So this is going to be the probability of one tail, order doesn't matter, plus the probability of two tails, order doesn't matter, probability of three tails, plus probability of four tails. Order doesn't matter in any of these cases. Okay. This is going to be a pain to try to calculate, okay, to try to do each of these things, right? Because the probability of one tail where the order doesn't matter, we did on the previous slide, and we had to do like 0.1029 times 4, and we had to figure out all those things, yeah? Like, we figured this part out, okay? This was on the previous slide, and we said, oh, okay, this was 0.4116 or something like this, right? This is from the previous slide. Okay, but then, you know, this is a, you know, more work than we want to bother with, okay? Well, we can also think of this alternatively, right? The probability of getting one or more tails, this is the complement. One or more tails. What is this the complement to? One or more tails is the complement of getting, so the complement means the situation where this did not happen. Complement of getting what? Yeah, of getting all heads or getting zero tails. Okay. One or more tails is the complement of getting zero tails. Okay, and that's actually true for all of life. Whatever it is that you can think of in your lifetime, that event will happen at least one time, or it will never happen. Okay, that's it. Whatever you can think of, whether it's I don't know, good things or bad things. Okay, in your lifetime, it will either, there's only two possible scenarios. It will either never happen to you, or it will happen to you at least one or more times. Okay, so so that's what we can think of here. Okay, what's the probability of getting one or more tails? That is the complement of getting zero tails. So we can calculate this and say, okay, the probability of at least one tail is equal to 1 minus the probability of zero tails. Okay, and zero tails means all heads, right? 1 minus zero tails, this will be 1 minus the probability of all four our heads. So we do 1 minus 0.7 raised to the fourth, and this comes out to be 1 minus 0.7 raised to the fourth, 0.75990, 0.7599. Is that okay? Okay, what if I asked you, what is the probability of getting at least one head? Getting at least one head. We won't make a clicker question out of this. We'll just say, what is the probability of getting at least one head? Let's see, what is probability of getting at least one head? Okay, so again, 4 flips. Each flip, the probability of heads is equal to 0.7. So what's the probability of getting at least one head? Probability of at least one head is going to be the complement of what? Is 1 minus the probability of getting zero heads, right? Either it's going to happen at least one time, or we get it happens no times, okay? So the probability of zero heads is going to be 1 minus the probability of 4 tails So I get 1 minus 0.3 raised to the 4th power, and that's a pretty small number. 1 minus 0.0081.9919. Okay, so this is going to happen with about 99% probability. It is possible to get 0 heads, but it doesn't happen very often. Okay, so if you flip the coin 4 times, there's about a 99% chance that you're going to get at least 1 head. All right, we'll end here for today, and we'll see you guys on Wednesday.